first project I worked on for Intel, we had the tagline, building blocks for gigaflops. Because if you hooked enough of our chips together, you could get a gigaflop, and that was revolutionary. You're starting on the verge of exascale. I will ask you, in 30 years, where will the industry be? You have no better idea of where you'll be in 30 years than I did 30 years ago. It's an amazing ride. I hope over the next few hours, few sessions, that I'll convey some of my enthusiasm for computer architecture and programming and help illustrate some of the questions or some of the challenges and questions before us and give you some attitude, because I don't think it's very useful for me to be up here and not share a little bit of my biases and beliefs. So hopefully that'll come through. I don't mind questions during the session. I may guide you to wait till the end, but feel free to interrupt me as I go through. Yes, I do enjoy teaching. I wrote one book about, 12 or 14 years ago and swore I'd never do something that stupid again. And here I am, just finished the 8th book. Intel was generous enough to send out enough copies. Hopefully all of you got a copy at registration of my 8th book. It is about Knight's Landing. But I actually think of the book as being divided into 3 parts. One is about Knight's Landing's architecture, another is about parallel programming, and a third is something I call a pearls section, which is real-world examples. Because as a teacher, one of my fondest memories is a book called The C Puzzle Book. This is a very long time ago, but when I was learning the C programming language, and yes, this is before C++ existed, understanding the ins and outs of programming thoroughly was important, and there was a book that Kernighan and Ritchie, based on a class that Kernighan and Ritchie did, and they just showed little programming examples that would mess you up if you couldn't read them. And so a couple of the books that we've come out with the last couple of years are called High Performance Parallels and Pearls 1, and then a volume 2. And each of them have about 25 real-world examples of code that I was blessed to get the authors to expose, show the code, talk through the changes they made to make it higher performance. And to me, those are the things I learn best from, is looking at other people's code. And you can imagine in 27 years at Intel how many people showed me their code and I got to work on or help them with it. That's the biggest source of learning for me. So if that resonates with you for learning, perhaps you'll get the opportunity to either look at the Pearls chapters in the Knight's Landing book that you each got, or look at a couple of the Pearls books we published the last couple of years. I'm hoping those are kind of timeless examples because they give you insights into what people do. And one of the things I've learned is that things that seem really hard, once you understand them, don't seem so hard. So if you go look at what other people do, and I actually got some of the authors to explain mistakes they made. I would always interrogate them and say, well, I don't want you just to say you looked at this code and you made this change and wow, look how smart you are, but how many things did you try that didn't work, and why did you try them, and why did you make those mistakes? And hopefully those come through. Now, this is the book that we were able to get copies for each of you on, and hopefully you find that interesting. It's funny, the first book we did on the Knight's architecture, Jim Jeffers and I put this book together, and when it came time to do cover art, we let an artist put a star scene on it. But I have no idea where the star scene came from. It was something they downloaded off the internet, and it's lost forever. The second book, the first Pearls book we did, we took an actual photo of the first machine on the top 500 list that used Knight's Corner. So that seemed cool. And then I saw an article. Neil deGrasse Tyson's kind of outspoken sometimes, and he criticized the movie Titanic because there's a scene with a star scene in it, and the star scene was not only inappropriate for 1912, but it was apparently inverted, so it wouldn't have ever happened in the night sky in the history of the world. And he criticized that, and James Cameron, the movie director, actually heard this and was a little annoyed by it, but told Neil deGrasse Tyson if he'd get him the correct star field, he'd put it into the special edition, 10th anniversary or something like that, Titanic edition, which they did. There's a whole bunch on Wikipedia about how he still got it wrong. Anyways, this kind of inspired me that our covers ought to have something on it that actually came from work we did. So the second Pearls book has, and I'll talk a little more about chapter 10 in this particular book, but it's some work from the University of Cambridge, the Institute for Theoretical Cosmology, Stephen Hawkins' team, and this is an image of Planck satellite data. It's a very amazing application of HPC to help try to understand the origins of the universe. So we put that on the cover, and then the book you have now, the KNL chip is not actually on fire. This is the marketing team at Intel worried about this, and I said, no. It's a cosmic web gravitational filament, which after we selected it, gravitational filaments got in the news, but we had actually selected it for the cover ahead of time. So the cover designs have some fascinating things, but bottom line is the thing that fascinates me most about computers, even though I've spent most of my time doing computer architecture and worrying about how to make programming and tools work for them, what fascinates me the most is what they get used for. And hopefully what I can share with you will help you go use these devices to do something amazing. Now, after all this fun HPC, my daughter, who's an engineer at Stanford, an engineering student at Stanford, this is her favorite book cover that I've ever done because her favorite movie in the world is How to Train Your Dragon. And somehow I got the folks at DreamWorks and Pixar to agree to have images from their movies on the same book cover, and that may be one of my better accomplishments in my career. But anyways, computer architecture is really fun again. And I say this because I started out my career with a simple premise. Silicon speeds weren't getting faster, and we had to use parallel computing. And that was in the late 80s. And there were technologies like systolic arrays being explored and so forth. And it turned out that there was a little life left in silicon and increasing the clock rates, because the amazing clock rates of 10 gigahertz, it turned out we could go faster, or 10 megahertz, I'm sorry. It turns out we could go faster than that. We could get into the gigahertz eventually. But then around 2004, that kind of petered out, and we're back to parallel computing and really focusing on the architecture of the system, all the things we can do, what can we push on. But to me, the desire here is to push on architecture but still keep the machines programmable, make it possible to write a program that lasts a while, that has performance portability. And hopefully some of my thoughts on how that happens or can happen will come through. But there's lots of different things in flux, whether it be memory systems or integration, different programming models. The debate whether we should have a very restrictive programming model that's close to the hardware, that gives us some level of control, or whether we should get more abstract and yet not necessarily match the hardware as well. In any case, if I had to encourage us to do one thing, stay very inquisitive as engineers. Don't buy one opinion from one person. Actually, I spent the last week in Detroit, and one day I went down to Greenfield Village, and I was in the Wright brothers bicycle shop, which is there. If you've never been to Greenfield Village and you find yourself in Detroit wondering why on earth did you end up in Detroit, I highly recommend going there. But one of the things the Wright brothers story emphasizes is that everybody knew how to fly by the time the Wright brothers flew. There were lots of books and theories and drawings, but no one had quite gotten it to work yet. And the Wright brothers frequently commented that, yeah, there was lots of writing on how to fly, but 90% of it was wrong. They had to go back. And so look at all the advice, look at all the things we've discovered in high-performance computing up to this point, but always question what's changing. The biggest change today versus the beginning of my career is at the beginning of my career, I spent all my time worrying about how to minimize how many computations a computer did. That was my, how I optimized a program. Today, I spend all my time trying to figure out how to minimize communication and data movement, and flops are relatively free. Now that's a bit of an exaggeration in both cases, because making either communication or flops go down can improve the performance. But today, being innovative at how to get rid of barriers, how to get rid of moving data around communication, there's still an enormous opportunity in redoing algorithms, redoing our thinking to reflect that. We barely scratched the surface. So staying inquisitive and looking at things, but always asking, why did someone do it that way, and is it still the right answer? Is it still the best answer? Anyways, computer architecture. I think it's fun again. Some people might say it's out of control, there's so many changes. But let me suggest there are three really big debates changing our lives today. One is, as we look at how to design a machine, should we be building compute elements, whether you call them nodes or CPUs or whatever, GPUs? Should you have a huge number of them, each lower performance, or should you have a smaller number of them, each of them higher performance? And there's just incredible engineering trade-offs there. And if you understand those trade-offs are being made, you'll understand a lot more of what's going on in the industry when you look at Intel versus ARM versus NVIDIA versus IBM versus AMD. You'll understand a lot of what's going on if you consider that trade-offs are being made. As opposed to thinking, gosh, one of these guys got it right and one of these guys got it wrong, you might think that they're aiming for a different engineering design point. Now, ultimately, some of them will be better than others, but this is a trade-off, and I'll show a little bit more on that in a moment. Also, should you go after being higher performance but more niche, or should you be more general purpose but give up some performance for that? A classic question. And the reality of today's HPC, and it will be, I think, permanently, is we need to use, we're better off using high volume parts, parts that have some that aren't designed just for HPC. Now, thank goodness big data has come along and data centers and so forth, because there's actually not very far from HPC is people building very large compute centers and worrying about many of the same issues. So saying commodity parts doesn't mean that we have to use the processors that are in tablets or our PCs. We actually have the opportunity to use infrastructure being built for big data centers and so forth. But we still need to use things that have other purposes other than just HPC to get the best economics. So that's an interesting trade-off, right? But how niche can you be? And working at Intel, I got the opportunity to see us debate processors versus GPUs versus FPGAs and have all of them in our product mix. And FPGAs look so niche, but they are coming of age now, and we may see them have enough volume to be in widespread use. They're already in widespread use, but we'll see even greater and greater use of them. And I would have said 10 years ago they were so niche that we'd probably never see them in HPC. But times have changed, and that's exciting. But they definitely are very, very niche in terms of programmability. And then finally, this memory compute, and I'm only going to brush the surface of that. I'll talk a little bit about some decisions we made in Knight's Landing and hopefully add a little color to that. So I think these are three really big things that are incredibly important to understand in computer architecture today, because these are things that are moving targets. These are the things that, if you really understand the debates that are going on and the things that are going to shape the future of computing going forward from here, I think these are three big ones. These are Incredibly important debates, and anyone that tells you they know the answers, the exact answers to how to solve any of these, well, they're being very hopeful at a minimum. Now, there are three things really affecting these debates. One of the things is that a megawatt per year of power costs about $1 million. So a 20 megawatt machine, just turning it on and operating it's going to cost you $20 million for the computer. Now, the rest of the compute center and stuff, add another 20 to 80% depending on the efficiency of your compute center. And if you've parked it far enough in the Arctic Circle, you may not spend as much on cooling. You may just help melt the ice cap faster. I don't know. But these things are, these are very real challenges. And by the way, it costs way more than $1 million a year in some parts of the world. But those parts of the world are less likely to put a compute center in. Coding is extremely expensive. Writing code, maintaining it, developing it. The number of people that can program at this level is small. And one of the complaints I hear about, very practical complaints I hear about using certain newer languages or more difficult programming techniques, such as CUDA, but I can say the same thing for vectorization, really effective vectorization on x86, is that there are less people in the world that can do that. And the good news is this is the crowd, and they can command a little higher salary. And people who are trying to write applications wouldn't mind if they could find programmers that were lower costs and hire more of them. Some of it's not just the cost, it's the availability, right? If you want to go hire a team of people to do this. So coding's expensive, and so balancing that, I've worked with plenty of architects that have brilliant ideas, but we'll be sitting around going, I don't even know how I would teach programming for this. Maybe I can get 10 people in a room and for a few weeks and get them excited about it. But I hope to have tens or hundreds of thousands of people programming a device very quickly, not just 10. So coding is a challenge as we look at the different architectures and how do we make them doable. And FPGAs, this is going to be a real challenge with FPGAs in that I can definitely teach how to program and use an FPGA, but it doesn't map onto most people's programming experience. So it's much more expensive to teach most programmers than other techniques. And then finally, performance portability. It was touched on last night. I think this is a great way to start a bar fight, especially if it's HPC programmers, even trying to define performance portability. My definition of performance portability is finding some way to write an application so that when you run it on two different architectures, you're achieving a similar amount of the performance that reasonably would be expected if you had written specially for those machines. So if you can get 60% on NVIDIA and 60% on Intel of what you would have gotten if you hand wrote for each one of them and spent a huge amount of times, that's performance portable. If you got 80% on one and 20 on the other, I don't call that performance portability. Unfortunately, when you look through the marketing from various companies, you might get a little confused when someone asserts that something runs just fine on a competitor's architecture. They might be saying it gets 20% over there while it gets 80% on my architecture. It gets a little confusing. So performance portability is a challenge. Now, I don't believe for a moment that the best approach to performance portability is magic compilers. I think the way you structure a program, the way you take the performance critical parts of it and make it portable, it may actually map down to a library or a technique or something that you actually do port from machine to machine. But the question is, can the overall architecture of your application survive from machine to machine? This is incredibly important and incredibly difficult to figure out. Part of it is a guess at where computer architecture is going to go in the future. Because if I suddenly give you a machine that has an FPGA in it and I can really accelerate a certain type of code, did you write your program so that certain type of code is available to be rewritten, or is it scattered all over in a way that you need to restructure your program? Computer architecture and performance portability play together. And there's no easy answer. Now, Moore's law. even though I'm not at Intel, it's no such thing as an Intel talk if you don't give homage to Moore's law. And we've seen processor clock rates stop around 2004. We can actually build faster processors. No one would buy them. Their power consumption goes up, but the performance doesn't go up enough. And so if I can give you a chip that consumes twice as much power but only gives you a 10% boost in performance, you're not going to buy it, not at $1 million a megawatt. So this is really the problem that I ran into, is not that we can't build the devices faster, but when you do build faster transistors, the memory's not keeping up in performance, the network, and the power consumption goes up without you finding a way to architect a machine that's faster. Now, you do see some creep in the clock rate going up, and it is possible to build faster devices still. In fact, there have been some revolutionary things happen since 2004 to reduce power leakage in chips. But clock rate in general is not probably ever going to go back on that curve of doubling every couple of years. However, the number of transistors on a chip continues to be able to be expanded. Now, when will this end? Every day we get a day closer to when it'll end. I have no idea when it'll end. Predictions of it ending have been going on a long time. There are physical barriers that probably catch up at some point. And then the question is, how do we cheat and move on? But the ability to integrate is still there, and it's still going to be a driving force over the next decade, the ability to integrate more because you have more transistors. But it's not clock rate. It's things like parallelism. It's things like the number of cores, the number of threads accelerating on a chip, the width of the computation, so the width of SIMD. So on in the Xeon Phi family, the SIMD instructions are 512 bits wide worth of data, so 16 single precision or 8 double precision numbers per instruction can be computed. And so these things are things that have been done with the extra transistors. And I'll mention a few others, like integration of the fabric onto the chip is another possibility. So Moore's law continues to give everything made out of silicon the opportunity to go forward. Now, I always was amused at Intel. I would talk to press sometimes and analysts, and they would say, well, now that Moore's law is dead, well, of course, I'd have to fix their opening sentence and tell them it's not dead. They'd say, wow, that really hurts Intel, but all your other competitors are going to be doing great. And I'd say, but they build things out of silicon too. If you're building something based on transistors and Moore's law stops, it affects everybody. There's no magical equation. The ability to have more integration and more transistors on a chip is an industry-wide gain if we can keep it alive. It wasn't something unique to Intel, even though Gordon Moore worked at Intel and came up with this law. It's something that affects all silicon. So I would always be amused with some of the analysts that would write articles saying, well, now that Moore's law is dying, that's going to really hurt Intel, but the other guys, their chips will be more popular. I just kind of blew my mind as an engineer. So real quick, look at computer architecture and think about it, and it is an integration story. So we've got, a long time ago, we had CPUs and they connected to memory, and it was really easy to figure out performance because every instruction would go fetch, an instruction would be fetched from memory, it would be decoded, it would go fetch the operands from memory, decode, it would operate on them, it would write back to memory. We kind of, screwed that up a little bit by adding caches, but if you took a look at the fact processors were getting faster and memory wasn't, the caches got injected. And the caches have a higher bandwidth connection, a higher data rate connection to the CPU for a variety of reasons. They're usually closer, nowadays often on the same chip. Memory's further away, usually still off chip or at least off package. And as time went on, some cache is good, more caches are better. one of the reasons that I think I've done very well in my career at understanding the performance of computers, and I compare it to other people who do very well, is that I'm fascinated with the engineering choices that are made here, right? The L1 caches are usually smaller than L2, and sometimes I get asked why, and it's, well, if you actually look at the design of an L1 caches might be 24 or 48-way associative these days, and that means that and they may be able to be multi-ported, meaning, or they are multi-ported, meaning several requests can be made and satisfied in the same clock. Well, to do that, you've got a vast array of circuitry going in to access the data. And instead of just having a bunch of data, you have all this extra circuitry making it so you can access it in parallel. And so the number of transistors needed per kilobyte or megabyte of data is much higher than it is in something like an L2 cache that has less ports, less associativity. It's just a simple design problem. So you've got these trade-offs. We can build bigger L1 caches. It just takes more and more and more transistors. And actually, one of the things that has happened with Moore's law and the slowing down of clock rates is the cache sizes have tended to get larger, because it's kind of a cheap thing to do, and it does benefit most programs. Unfortunately, there are some very badly behaved programs, and probably a bunch of you get to work with them, that caches don't help as much. But in the big world out there, caches do help. And L1s and L2 caches have grown enormously in size because of the transistor capabilities. There's even some capabilities in some of Intel's Xeon processors now that we call transactional synchronization extensions that are able to help implement some of the primitives for transactions on memory. Those take more transistors in the cache too. If you ever ask a Xeon Phi developer why transactional synchronization instructions aren't supported in Xeon Phi, they'll either tell you one of two things. They'll tell you we don't think they apply as much in HPC, which I believe, or they'll tell you it would have taken extra transistors. We would have had to throw in a few more cores off the chip. So nothing comes for free. We can make these caches more and more sophisticated with capabilities like that, and you'll see that. Even memories are going to get more complicated what they can do. But anyways, eventually these caches move on chip. Along come coprocessors. Coprocessors have been around a long, long time. Some of the earliest ones were floating point coprocessors. The original IBM PCs had an option to stick in an 8087 and as a math coprocessor because it didn't have floating point built into the hardware originally. Those two we eventually integrate onto the chip because it's a good idea. And we've seen even coprocessors like GPUs, also the opportunities there to integrate those onto the chip. So lots and lots of integration over the years onto processors. And now with the initial Xeon Phi was a coprocessor card, but with Knight's Landing, essentially we've integrated that onto the chip as well. And so we've got really exciting different types of nodes we can build today. We can build nodes with coprocessors. We can build nodes with just CPUs. We can have GPU cards. We can have integrated GPUs. There's a lot of variety. And then, of course, we can talk about clusters. And we can even integrate the network controller onto the chip now, which is what we have with some versions of Knight's Landing. So integration, integration, integration. And I will say the integration of the NIC is an interesting thing. At the risk of not completely agreeing with the former speaker made a little comment at the end that integration doesn't help latency. Actually, it does, but for an interesting reason. It doesn't help latency by the signaling, but when you make the NICs more and more complex, they can do some things that used to be in software. One of them, for instance, is things like tag matching. which is usually a software task. But if you put that in hardware, you can actually reduce the amount of involvement the CPU has in implementing a protocol. And one of the ones that fascinates me a lot is PGAS. So PGAS is this brilliant concept of a way to make things more programmable that has been on posters for every supercomputing that I've ever gone to. So I'll go to the supercomputing conference, and there'll be people supporting PGAS, and they'll have their posters, and they're in a corner, and you always ask them, when's this going to take off? And they say next year. And it's been going on for 20 years. So when I decided that I wanted to put a chapter on PGAS in the Knights Landing book, some people at Intel told me I was insane. Did I lose it? And honestly, Knights Landing's probably not quite the place PGAS takes off, but we're on the verge of it. I honestly believe that because NICs are integrating this, they're going to drive down the effective latency of protocols. And one of the sea of changes we're going to see is I think PGAS languages suddenly come of age. I think that one of the frustrations of using PGAS languages is if you use them very carefully for particular problems on particular hardware, especially if you have something like a Cray Aries fabric, which is very low latency, has already driven this way down, you can get fabulous performance. But if you just kind of casually use PGAS and you think you're going to get great performance, you'll suddenly find out you needed to know more about the fabric and the latency than you anticipated. I think that's going to be greatly relaxed. I'm not saying that PGAS will suddenly be easy to get amazing performance on, but I think it will become much more competitive with other techniques. Now, MPI, with its latest standard, has effectively become a PGAS programming method as well. So you've got that, you've got co-array Fortran, you've got UPC. But in any case, PGAS, by the way, I'm sorry if I'm losing you, PGAS stands for Partition Global Array, and it's just a view from a programmer's view that you can have a data structure that spans all your nodes, but obviously the processor can only directly address the data that's on your node, but that if you actually address data that's on another node, something mysterious will happen underneath your programming model to go grab that data or to update it. And if you program carefully using PGAS, you can get some very readable programs. Anyways, there is a chapter in the Knights Landing book because I'm a believer that certainly over the next decade, we're going to see a big rise in PGAS usage. Or I don't think it's going to replace anything. I think it's just going to become a very viable alternative on a very wide array of architectures, not just Intel, but a very wide array of machines, and that'll make it a viable way to program. Now, PGAS is extremely popular in some areas. So CFD users on Cray like it, and there are some very dark people that don't talk a lot that use it a lot for applications. So PGAS is already popular in some very limited domains, and I've gotten to see that and see why it's popular for them, and I think the changes in hardware architecture will make it popular for more people. So let me say a few things about why Xeon Phi. Now, this gentleman, Seymour Cray, did not believe very much in parallelism. And he had a very funny saying. Being from Minnesota, being from the heartland of the US, he liked to make farm analogies. And he would ask the question, would you rather plow your field with 2 strong oxen or with 1,024 chickens pulling the plow? And that always got good humor. And obviously, he wasn't a big fan of 1,024 chickens. Now, I don't think a Xeon Phi or an NVIDIA GPU is 1,024 chickens. It's probably not either company's marketing terminology for their architecture, but this is what's happening. It really is the debate about, can I design a plow that's pulled by 100 or 1,024, a plentiful supply of chickens, rather than more difficult to obtain oxen. And so, if you take a look on a piece of silicon, we can design a handful of Xeon processors or a much larger number of Xeon Phis. And the reason is the Xeon processors are designed to do everything. They can run a serial program well. They can run a parallel program. They have all sorts of things. They have, basically, there is an out-of-order execution machine with larger tables for everything, so that no matter which way your program's unbalanced, the Xeon tries to make up for it. On the Xeon Phi, generally that was thrown out. A lot of the things that make it more tolerant for programs that haven't been written for parallelism, we throw that out on Xeon Phi and greatly reduce the size of the processor, an individual processor, but effectively reduce its overall performance at the same time, but we can put a lot more of them on a die. Now, this debate's been going on a long time. I remember multi-flow machines and machines before that, Josh Fisher's connection machines, which had, little bit slice processors and thousands of them. This debate's going to continue. Are you better off cramming a lot of less capable devices in a space, or a few more capable? I'll tell you what, the larger ones are generally more programmable. They're more forgiving to programming. But you know what? If you're going to write a parallel program, do you really need that, or are you better off with a smaller number? And this is really what motivates Intel to have Xeons and Xeon Phis. The idea that somehow we can take and strip down the design of a processor and cram more of them on a die, and that for a parallel program, for a parallel application, give you higher performance. And I drew this picture for the first book because after a few years of teaching the programming for this before we came out with the first Xeon Phi, I started to realize one of the things people did not get was that the Xeon Phi's performance per core is lower, and so you actually need a parallel program. So if you show up and say, gee, I'm going to run a 10-threaded program, a program with 10 threads on your Xeon Phi, how will it perform? I'll say terrible. Because we've got over 100 threads, but 72 cores in the latest one. And you're better off on a Xeon if you're only going to have 10 threads, right, in general. The key, though, is that you need to know, can you create that massive number of threads? Now, if you program GPUs, it's the same thing, right? A GPU is not going to run well if you show up with 10 things to do. You have to think massively parallel. So this is the opportunity architects are giving us, which is that we can design processing capabilities that rely on us being able to find massive amounts of parallelism. If we can find it, it can be rewarded better by devices that have been designed for the parallelism, that have that 1024 chickens. But if we can't, we're better off on a more standard device. And so this is really what Xeon and Xeon Phi is to Intel. Now, the big difference with Intel presenting Xeon and Xeon Phi versus competitors is it's the same programming model. It's the same tools. It's x86. And that was not easy to do. And trust me, there's intense debate inside Intel whether that was the right thing to do. You'd think, well, of course it's x86. It comes from Intel. But you've got a bunch of engineers that want to design the best processor they can. And sometimes they see the opportunity to break compatibility and beg forgiveness. And we come up with things like Itanium. But x86 has served Intel very well, and Xeon Phi has that. Now, Xeon Phi is lots more on a die, each of them less performance. And perhaps this is a little bit more niche device, right? It will not run an Apache web server quite as well. Although it's getting close. I'll show you some data. But that's not its target market. And Xeon Phi is more power efficient. It does address the coding because it is programmable exactly the same way as a Xeon processor. And performance portability between a Xeon and a Xeon Phi is very, very high. At least any optimization you do for either generally affects the other. So while you may not have performance portability to start with, there isn't any necessity of forking your code to keep it performance portable between the two. And that was our vision putting together Xeon Phi. Now, I wanted to talk a little bit about Xeon Phi. I'm going to run up to about 10:30. Like I promised, I'd be a little bit late, but we'll have our break last for a half hour after that. But let me talk a little bit about Knight's Landing, some particulars about it, give some insight into design that we did. This is now if you want more depth than I have here, Chapter 2 of our book gives an overview of Knight's Landing, and Chapter 4 is the in-depth deep dive, and then Chapter 6 goes into micro optimizations, which will give you even more insight into the architecture if you want. And Chapter 6, and Chapter 5 is about OmniPath. In any case, you see this nice photo. Here's one thing I can do with a screenshot that help drive home the photo and the diagram we use are very similar. The diagram that the architects use is motivated by the actual layout on the chip. And what you'll see is a large number of replicated tile. And each tile on the in Knight's Landing has 2 cores on it, and the cores share an L2 cache. Or more appropriately, they share part of the L2 cache, because the L2 cache is distributed across all the tile. There's a local part of it and a far away parts of it. And then each core has 2 vector processing units. So these are where the SIMD instructions execute. And then there's a CHA, and the CHA is what connects the tiles together. It's the caching home agent. In any case, let me show you a few things. So Intel's put out different benchmarks. This is in Chapter 1 or 2 of our book. It shows performance versus a Xeon processor. It shows performance per watt. And the performance per watt is generally higher across the board. And you see a lot of usual suspects. You see LinPack, and you see some machine learning applications and different Trinity apps and so forth. The two that I wanted to highlight, though, that kind of are interesting because you don't usually see them in HPC workloads, SpecInt rate and SpecFP rate, which is, these are more workstation workloads and more not as parallel. The rate means how many can you run simultaneously. But this is the thing that hints that this Xeon Phi is very different than the one before it. It's actually quite capable at running workstation workloads or even maybe an Apache web server. That's not its main target market, but the fact that it can be competitive with a Xeon processor, a little bit better on SpecFP rate, on everything. On SpecInt rate, it's a little bit faster, but just a tiny bit less power efficient, which hints at the fact that it may not quite be ready for Apache web servers, but because of the power, it may be a little higher power. But this is interesting. It's interesting that Xeon Phi has gotten close enough to Xeon to be competitive on these metrics. It says a lot for how fast the Xeon Phi technology is maturing. But the tile, let me talk about the tile a little bit. The tile on Xeon Phi on Knight's Landing has full support for the vector instruction sets of all the prior x86 machines. So MMX, SSE, SSE2, SSE3, SSSE 3, 4.1, 4.2, AVX, AVX2 are all on the chip, even the BMI instructions out of AVX. And then it adds AVX 512. So it can do 512-bit instructions. Now, If you use AVX instructions, which are 256 bits wide, you'll get about half the performance that than you would with AVX 512 if you are limited by your computation. Now, a lot of people have seen on Knight's Landing that they can get 90% of the performance on AVX if they're actually more bandwidth limited. And so your mileage may vary. So you can take a binary that runs on a Haswell processor, for instance, and run it on Knight's Landing. It will run unmodified using AVX and sometimes is quite performance competitive. Your biggest bottleneck really is whether or not you need the AVX 512 to get the full performance. But the code moves back and forth. Now, one of the features Knight's Landing has, and this is sort of a hint at where computer architecture is going in the future, is we have an on-package memory. Now, I'm very well practiced, having been at Intel, at saying the difference between on-package and on-die. So if you hear someone that's very careful with their words, on-die or on-chip would mean it's integrated on the same silicon. That has a disadvantage of that there's a set number of transistors we can fit on a chip. The reticle limit of the process technology says we can image a die a certain size. It's the maximum number of transistors. So if we try to cram more things on a die, we actually have to kick some features off to put other features on. So if we were to have put the memory on the same die, we would have had to kick off cores. So what you have is you have Knight's Landing with 72 cores is the maximum number of cores we felt we could fit on the device. And then we have 16 gig of memory, which is a different chip, but they're on the same package. It's actually a set of chips stacked on each other and then connected to the CAN-L die. This MCDRAM, as it's called, could just be used as a cache. Or it could just be used as a memory, or it can be used as a combination. And this is an interesting option that the architects put in Knight's Landing that give you a lot of versatility. So you've got this 16 gig. It's really, really close to the chip. It's on the package. And first of all, you can use it as a cache. It's a memory side cache. Go back and look in your computer architecture textbooks to remember what that is. But it means that you actually don't need to snoop onto the, you don't need to snoop it. It's part of the memory from that perspective. So it can sit there and be a cache. And it turns out this is usually the best way to use it for most applications, especially a cache-friendly application, because the cache will get fully used for the data, the instructions, everything that affects your performance. But you can say, hey, don't treat it as a cache. I want it as a 16 gig memory. And if you do that, you as an application writer are responsible for using it. I can promise you, if you only use a small part of it, you're probably hurting yourself on performance versus using it as a cache. So your challenge, if you take overall 16 gig, is to actually use it very effectively for your application. And
there's been some discussion that you can only make this choice at boot time.
Correct. So I'll speak to that in just a second. And then then you can have a hybrid. You can say use half as a cache, half as a memory. And this is done, these different options are done at boot time in the BIOS. Actually, I never do it this way. I use command line tools to change the BIOS options. The reason is I don't want to boot into the BIOS, change it, and reboot again for it to take effect. I just do the command line things and do a reboot. And then you can partition the memory. So let me speak to how to use it, and then I'll speak to why it's a boot time option. So if you've said, hey, I want to use it as a memory, then it becomes a high bandwidth memory. It's actually not faster than memory. It's higher bandwidth. That's an incredibly important distinction. The latency to memory is actually technically a tiny bit smaller, but you'll never notice that. But the latency is about the same to go talk to the MCDRAM on package or go off chip. But the thing is, if you're using the MCDRAM, the on package memory, you can get more requests satisfied per clock. So if you have a program that is bandwidth limited, it will get better performance out of MCDRAM than it will out of main memory. And that's why it's there. It's a high bandwidth memory. It's a high bandwidth local memory, 16 gig. The way you program it is basically there are different forms of malloc and different ways of allocating in Fortran that say, hey, try to give me memory out of high bandwidth. Now, chapter 3 in the book goes into excruciating detail, and it's one of the chapters that I wrote. So chapter 3, if it's not readable, that's my fault. That chapter I found very challenging to write because it was very poorly documented in the early days of working on Knight's Landing, how we were going to do this. But the idea is pretty simple. You change your program to allocate out this memory. Now, we've actually got some clever tools that will actually, you can do an interposer, and you can say, hey, allocations of this size, I want them to go to high bandwidth memory. And you can actually run unmodified code because the interposer can intercept malloc calls of a certain size and rearrange them. So anyways, chapter 3 goes over that. But ultimately, you are changing to use the memory by changing your code to do something like change a malloc to a fast malloc or MCDRAM in Fortran. Now, I didn't get to cluster modes. I'll do that when we reconvene after break. But let me talk about the question that was asked here about it being boot time. So what you have is you have a processor with a memory on top, on package. And you want to use it as a cache, or you want to use it as a memory? Well, there is no application out there that I know that could survive me suddenly saying, oops, I deleted some memory and added some cache, or vice versa. And so if we were to be able to change this without rebooting, at a minimum, I think I'd need to shut down applications. Well, it turns out there aren't any operating systems out there that really can survive that type of reconfiguration. Maybe in the future there will be. But then on the chip itself, the chip is doing these decisions. Like when you go access a certain range of memory, it has to decide, where is that memory? It's built up tables, shared them with the OS. It doesn't know what the OS has done with them. But let's say that the OS and the applications knew what they were doing if we were to switch cache between cache and memory. On the chip itself, we've got tables. We've got tables about what's cached where and so forth. And we could have designed the chip so that you could say, hey, I want to switch from being a cache to being a memory. And what we'd have to do is walk the cache, flush it, change it, shut it down, switch it to memory, map it in, inform the OS, all of that stuff in hardware. Two problems. One, it takes transistors, and we would have had to kick off a few cores. And two, it's very buggy, very error-prone, and it takes time. That type of walk would shut the chip down, install it. So we made the decision that since no applications and no OSs could survive this, that we wouldn't make it so that the chip could even try. So the way that you do that is you reset the chip, and the chip comes out of reset. And it does that reasonably fast. So there are two different things that can be changed in a Knight's Landing. The second one I'll talk about after the break, but the first one is whether your on-chip memory is cache or memory or a little of both, and the other is the cluster mode, and I'll talk about that after break. Both of those are only changeable by resetting the chip. And I will stand behind saying that resetting the chip was the right choice. It gave us more cores on the device, reduced the complexity of the device, And even if we had tried to tackle this, there isn't any technology in today's OSs to survive those sorts of things changing out from under the OS. So we would have had to reboot the OS anyways. Now maybe in the future, if these sorts of options are critical and we decide that these different modes we need to switch back and forth, we can learn from that. So the way I view KNL and actually future versions like KNH is that we're going to get experience about which applications should run in which modes. We may get a better idea if we want to switch more rapidly between some of them, and we may figure out how to design the OSs, even the applications, to survive those changes, but that's not in today's chip. Now the good news, you can change these things. I'm used to designing a computer, a supercomputer, and saying, should we have cache or should we have scratch memory? And I was always in favor of cache, so we'd put cache on. Or how do we do the interconnect between the chips? And I'll talk about the cluster modes in a little bit. And those would be hardwired, and you couldn't change them. We would just teach you that's the way the architecture is. So Knight's Landing makes it a little more exciting in that we've got 72 cores, but we will allow you to change how the on-package memory is considered, whether it's cache or memory, and we'll allow you to change the clustering modes by a simple reboot. And that's more configurability than I think we've ever built into a machine of this type before. And so we'll start from there and decide if more things are warranted.
James, have you met anyone who has a code that satisfies your definition of performance portability? And if so, what did their code look like? What application was it? And what platforms were they running on?
I have, as long as the machines they want to be performance portable on are processors, whether it be Intel, AMD, IBM. GPUs have thrown a wrinkle into this in that the approach of writing a program for a GPU and a CPU are generally divergent. I've seen some codes that use GPUs that were designed for CPUs from the get-go and sort of fit the GPU code into that, and they've remained performance portable as well. Where I see issues is I see machines, I see programs written for GPUs that have not considered some of the things that arise with CPUs. I've also seen CPU code that didn't consider issues that arise with GPUs. And if you define performance portability as needing to bridge those two, that's a very hard problem, unsolved. The GPUs don't differentiate between threads and vectors, whereas CPUs rely very heavily on you understanding the difference. GPUs have local scratchpad memory texture maps that they use, but not caches as much, and need to be organized in a way to take advantage of that, whereas CPUs generally have relied more on caches and are very, very sensitive to latency more than GPUs. So those programming considerations are a problem. So absolutely, I see, I think a very large amount of code has been able to be, with OpenMP, MPI, be very performance portable across CPU-based machines. And the real challenge in performance portability has been the introduction of devices that are fundamentally programmed on some levels differently. And the structure of the program, the structure of a program to be best on a GPU versus a CPU can be very different. And if you're starting with CPU code, that's unfair to the GPU. And if you're starting with GPU code, it's unfair to a CPU. And I think that's where a lot of challenges are today. Throw FPGAs into the mix, it starts getting even more exciting. So I think that's a challenge of modern programming that has only recently arisen. And before that, I don't think we talked much about performance portability because you know, if my CPU started to not be able to keep up with IBM's, we would design our CPU differently, and IBM would do the same if we got ahead. GPUs and CPUs don't swap technology the same way. What makes a GPU fast is not the same as a CPU, and the programming forks, and it's not clear how to keep them how to keep them aligned without disadvantaging one or the other, right? So this just gives rise to very interesting debates, like OpenACC, unfortunately pitted against OpenMP, which isn't really fair, but OpenMP has a rich legacy, obviously, from CPUs. OpenACC is very, very targeted at NVIDIA GPUs. Anyone that tells you differently is you can target very specifically to something and then say, hey, what can I use this well on other things? And that debate's a fine debate, but very, very targeted to NVIDIA GPUs. OpenMP tried to be much more general purpose. Well, it's a classic engineering trade-off. When you try to be more general purpose, you're probably not best at anything. OpenACC is probably best at NVIDIA GPUs, at least one would hope so, and now on goes the debate. And you throw into that Michael Wolff's very strong belief that OpenACC should be more prescriptive and less, or more descriptive, less prescriptive. Those words to a compiler writer, when you describe a problem, a compiler then can do anything at once. If you prescribe very tightly as a programming model what you need to do, the compiler is more constrained at what optimizations it can do. Now, prescriptive programs tend to be more portable because once you as a programmer prescribe something, it tends to, from compiler to compiler, work similarly on that hardware, but it doesn't give the compiler as many options. So OpenACC elected to be more descriptive, which theoretically makes it more portable, but also makes it more difficult to keep compatibility between compilers. OpenMP has a long tradition of being prescriptive, which serves users well, but actually adapts to new architectures less well. One of the reasons OpenMP sometimes has challenges addressing new systems, new CPUs in GPUs. So there's a lot of things nuanced in trying to figure out the performance portability, and the debates that come up with something like OpenACC and OpenMP, if you understand what's really being debated at a technical level, they're trying, it should be an industry debate among users about what programming models will let me write a performance portable application. And the big issue is GPUs versus CPUs today in computer architecture. CPU to CPU performance portability is pretty easy. GPU to GPU isn't as easy. AMD and NVIDIA GPUs aren't identical, and Intel's GPUs are even more different. And you'll be frustrated trying to move between GPUs today. But that's anyways, hopefully that was a little bit useful. But yeah, the GPU CPU is the heart of the matter for performance portability.
So James, you just elaborated about this packaged memory. So is there a basic reason why packaged memory is now on the Xeon Phi, but is not on standard Xeon processors? And could this help?
Why is it on Xeon Phi first? Because the Xeon Phi team did it first. I can't pre-announce Intel products, but it's a reasonable guess that you'll see that pop up on other products from Intel, and I presume from others as well. It's a good idea. There isn't anything generic about Xeon Phi that says it has to be the only one that does this. I think it was for the particular market Xeon Phi's in, the need was there, the belief that people would buy it was there, and that's why it happened first. But I actually believe there's a lot of merit in putting it on Xeons and putting it on Power and maybe eventually ARMs and AMD processors as well. I think it's an architectural trend we'll see. And that's probably a really important point to make. That belief makes me say, hey, when you're writing your application, if you're looking at Knight's Landing and you're thinking, okay, should I recode my cache-unfriendly app to start managing its own local high bandwidth memory, you should ask yourself, am I only doing this for Intel Xeon Phis? And my personal belief is no, you're doing it for an architectural trend that you'll see pop up on other machines. Now, I could be wrong, but that's my belief, and so I don't think your effort to rearrange code and examine local high bandwidth memory, I don't think it'll be wasted. And in a way, texture map memory on GPUs has a similarity to this and maybe as we look at application portability, we'll find that those will grow up to be more similar high bandwidth local memories.
If we are having a FPGA integrated into CPU in the future, how would that look like? And now if we are doing some programming, designing a code, how do we take advantage of that maybe in the future to ensure portability into next generation of architectures?
So FPGAs, it's really interesting. FPGAs have a very big presence in the data center today already. And the way that the motherboards are designed is that you have the processors and you plop an FPGA basically as a device on the PCIe bus. This has been going on for a while. And so when Intel announced it was buying Altera, for people in the data center, that wasn't, it made a lot of sense. It caught HPC people a bit off guard, even at Intel, because it really hadn't been thought about in HPC a lot. I mean, it had been, but it hadn't been thought about, oh my gosh, we need to go integrate. But the FPGAs in the data center were being used and you can go read papers from Microsoft on their search engine, Bing, but eBay and search engines like Microsoft and Google have been using FPGAs to encode proprietary algorithms. And I think of an FPGA as a set of Tinker Toys or Lego building blocks for a hardware person. So it's like, I wish I had an instruction that did this, or I wish I could feed all these bits and it would do this to it and give me the answer. And I know how to do that circuit, but there's no instruction that does that. And that's how I look at an FPGA. Now, an FPGA, the best way to think about an FPGA programming-wise is it's a pipeline. You put in some data on one end and out comes an answer, and it's a pipeline. It's a bunch of circuits that you design to do something, and fundamentally, you're going to be feeding data in one end and out comes data at the other end. And if you can do something better in an FPGA, compute something faster or broader, it's an amazing way to go. The Xeons that will have FPGAs on them on package, there's several things going on. One, on package will reduce the latency, will help that, but mostly it increases density. So keep in mind in a data center, like a Google data center, today they have to have a Xeon and an FPGA package both on the motherboard. In the future, Intel will say, hey, you can just plug in a Xeon, it'll already have the FPGA in it. That increases density. The other thing is Intel said it'll produce the FPGAs on Intel process technology, which is a giant leap forward for FPGAs because FPGAs have not been being produced on the leading silicon technologies. So it'll reduce power, increase density, increase the complexity of the FPGAs over time. And that's a huge boost for FPGAs and what they're capable of. So it's a density play. It's a play at jumping FPGAs forward. But they're going to stay a device on the PCIe bus for the foreseeable future, I think. I don't think a tighter integration than that's not obvious to me. Now, perhaps, far in the future. But so I think for programming, you're going to mostly consider them a black box. You're going to have a function. So the way that companies like Microsoft and Google treat these is they treat them as an accelerator for certain functions. They come up with a library. Their applications call that library. And if there's an FPGA on the device, boom, it uses it. If there's not, they could emulate it. Now, I think in general, they deploy their software knowing whether it's there or not. But theoretically, it's a library you call that opportunistically can be implemented by the FPGA. And I think it's going to be that way for a while. Now, programming these, today the people that program them generally do it in VHDL or a language like that, a hardware description language. They tinker toy the things together. They design a circuit. So someone as a programmer says, I'd like to accelerate this function. Someone as a hardware designer designs the circuits that do that and put in FPGA. There's a lot of people believe that we can use higher level programming languages to program FPGAs, and that's theoretically possible. I think the question is whether it's efficient enough. If you're going to use an FPGA as an extra cost, at what point is programmer productivity more important than the productivity of the device. So I think VHDL is going to stay popular for a long time. Now, OpenCL gets mentioned a lot. OpenCL is really two languages in one. It's there's a networking sort of layer, a communication layer of OpenCL that says how things talk to each other, different modules, and then there's a programming part. The part, when people talk about OpenCL, they're actually talking about, for FPGAs, the part that excites them is that I can query as the device there, I can get connections to it, I can ship data, I can manage the data and the movement of things. How you actually program it, you could use OpenCL to talk to your FPGA and use it, and then use VHDL as the thing that wrote the code. So OpenCL is not a shoe-in as the programming method. It's more of a well-defined standard for communicating and setting up talking to it, which is incredibly important to understand because people start talking about using OpenCL for it and people think, wow, I should learn OpenCL programming. It's like, OpenCL programming is not that exciting. And it's actually not the, OpenCL is designed for GPUs. It's got a very heavy kernel focus. So you'll see that they're adding pipeline capabilities to OpenCL. And those pipeline capabilities, again, an FPGA is essentially a pipeline. So you're going to want to program as a pipeline. Again, this kills performance portability because you're going to program an FPGA as a pipeline, you're going to program a GPU as a kernel, and you're going to program a CPU a little bit different than a kernel usually. And so even though people say, wow, I'm programming all three with OpenCL, there's no performance portability. It's not abstract enough. It's too low level. You need something more abstract to get performance portability where you describe things at a higher level. If you're going to be describing as a pipeline for an FPGA, a kernel for a GPU, and something else for a CPU, you have no performance portability in your code. But who cares because these are pretty specialty devices. So hopefully that helps a little. It's density play putting it on. It's a process technology play to increase the capabilities. And then it's a PCIe device that's probably hidden behind a library interface to be used by the masses in the data center. And so this brings up an interesting question with HPC, which is if one were to build a machine, and I think people will, with FPGAs in it, who's going to program the FPGAs? Are you just going to have some libraries? How many people are really going to program the FPGAs? And are you going to change the FPGA's programming? Because the way the data centers use them today is some people, working on a search engine for Bing encode some of their algorithms, put it in the FPGAs, and they leave the data center alone. They don't change those job to job. The data center is running search engines 24/7, and the algorithms they've hard-coded stay there. But in HPC, if you had different workloads and each workload wanted the FPGA programmed differently, would you ever actually do that? People have been talking about reconfigurable computing for many decades. Quite a few of them from the University of Wisconsin-Madison is a hotbed for the last 20 years of talking about that. And maybe we get reconfigurable computing eventually, but that's not how FPGAs are starting. They're starting as a black box program once, use across the data center device, and that's where we are today, and then we can move forward. I talked about the MCDRAM because it's on package. I didn't mention there can be up to 384 gigabytes of off-package memory on a Xeon Phi. So the 16 gigs is just it's exciting to me because it's an architectural new thing, having a cache that can be pinned down and used as local memory on package. The other thing that's interesting as we venture forward and put this many cores on a device is how are they interconnected and how do they interconnect to memory? And this is a classic question we ask ourselves as architects for years do we do a shared memory system across all the cores, or do we divide it up into NUMA zones and so forth? And it turns out on Knight's Landing you have several options, and I wanted to talk about those. Because you've got all these each tile has 2 cores on it. How are they hooked together? Well, they're hooked together with a 2D mesh. And you can see there are 8 connections to the MCDRAM. The MCDRAM is actually a set of stacked DIMMs. There's actually 8 of them. So these little connections effectively go to different ones. The architects would scream at me for describing it that way, but it's close enough. And then there's 2 connections to DDR off of the package, actually with multiple channels. So for a given core, if it has a memory access, it needs to first figure out if it's in its local L2, then it needs to figure out is it in someone else's L2, and if it's not in an L2, then it needs to decide if it should go to MCDRAM or DDR. And so I'm going to talk a little bit about that because there were a bunch of choices, and the architects left some of them to be made to be reconfigurable again at boot time. So again, a BIOS option, and I go over these in, I think I go over these in chapter 4. I can't remember. They're mentioned in chapters 2, 3, and 4 of the book. The quadrant mode. So let's think about a memory access on the cluster. And this will give you an idea that any multiprocessor system is going to undergo this at some level. And understanding this can be really key to understanding performance on different machines. But Knight's Landing, if we start with a cache miss, a local, the core on a tile has looked in its L2 and says the data's not here. Now, effectively, it probably looked in its L1 first, and then it wasn't there. It looked at its L2. So it needs to find out where it is. And Knight's Landing uses a distributed tag architecture, meaning that based on a hashing algorithm, there is uniquely one tag directory somewhere on the chip that knows where the data is. So if it's not in my L2, there is one unique owner of knowing where that address is. And in this particular case, we have to route over to it. Now, the routing algorithm on Knight's Landing is Y then X, always. And so we go over to a tag, potentially way across the chip, and we look in that tag directory. That was the CHA part of the tile. And that directory will tell us where the data is. And it could either tell us it's in someone else's L2, in which case we need to route, pick that up, and send it back, or route the request there, or we need to go to MCDRAM or DDR. In this particular case, we get a miss, and we have to go talk to the MCDRAM that has the data in it. So we route over to the tile that's hooked to that MCDRAM up there, and it loads it from memory, from the MCDRAM, and then it has to route the data back. Now, this is an illustration of if we're running in all-to-all mode. The requester tile, if it doesn't have the data, can go to a tag directory, and that tag directory may be anywhere on the chip. And then the tag may return that the data is in an L2 or an MCDRAM anywhere on the chip. And then it has to route back. Now, I usually think of KNL Knight's Landing as having 2 modes, but there's actually 5. The 2 modes that are interesting to me are quadrant and SNC4. There's actually quadrant and SNC4 divide the chips up into 4 parts. There's actually a hemisphere and an SNC2 that only divide it in 2, but they're exact corollaries. And I can explain later why hemispheres might be interesting. But they're kind of degenerate. And then there's this all-to-all mode. All-to-all mode is only on the chip for one reason. If you don't plug in your DDRs to be evenly balanced, you have to be in all-to-all mode. Now, if you think like a chip architect, the job of our chips are to boot and come up all the time. And it's not okay for the chip to have made an assumption the DDRs will all be put in evenly. If one of them fails, or if you decided to configure your machine that way, the chip should still boot. And it has to boot in all-to-all. And the reason for that is because in order to support the other modes, the architects made assumptions about the DDRs being evenly just plugged in. so that they made a decision that the DDR channels are all fully populated with exactly the same size DDRs, and that does great optimizations for the tables all over the chip, for routing, for using certain bits in the memory addresses and always being able to hash it a certain way. And they came up with a totally different algorithm for all-to-all general purpose, but we really don't expect the chips to be booted in all-to-all. We don't expect people to build their machines that way. But if you do build them that way, they still work. And they're good performance, but it's, that's why all-to-all is there. And so what's this other mysterious mode? Well, if we go to a quadrant mode, what a quadrant mode does is it says, let's consider the chip to have 4 sections, but let's always make the tag directory that looks up things, have it be in the same quadrant as the memory request would go to for MCDRAM or DDR if it's not fulfilled. Now, what that does is it reduces slightly the distance traveled to satisfy a memory request. And that has 2 effects. The latency is not the biggest one. The biggest one is the latency is reduced slightly, but because the latency is reduced, the number of outstanding memory requests effectively increases. The number of outstanding memory requests at any given time is set, but if you can satisfy the memory request faster, you can get another memory request outstanding faster. And so your bandwidth goes up slightly when you do this. So in this particular case, we can go back to the same example. We have a cache miss. Here are the tags in the memory are affinitized. So we get a cache miss. The cache miss is 1. We go to a tag that's in the same quadrant. We go to the memory in the same quadrant. We satisfy it. We restrict our accesses locally in the quadrant. Now, I should say the memory remains coherent across the whole chip. So in quadrant mode, we don't, we still make all the memory accessible from any core, but when we go to look in a tag directory, the tag directory is always in the same quadrant as the memory. So that reduces a little bit. Then there's one further refinement we can do, which is the SNC4 mode. And what we do is we affinitize the use of the memory, the tag, and the connection to the memory all in the same quadrant. The quadrant mode is completely invisible to software. The affinitization of tags and memory, the reason I can do it is because I know my DDRs are plugged in evenly. In other words, the way that every machine probably is configured. And so quadrant mode is, by default, the way programs will run. This little optimization, not that important to know about as a software programmer, not important at all because it just works. It reduces the latency slightly to get to memory without any programming implications. The SNC, the sub-NUMA clustering mode, has program implications. We actually can operate Knight's Landing as if it had 4 NUMA zones, or 2 NUMA zones for SNC2. Now, a NUMA zone means that some memory is close, some is far. So this is really easy to use if SNC4 is really easy to use if you have a multiple of 4 ranks in your MPI program. If you've got 4 ranks or 8 ranks or 16, you just map some of the ranks to one quadrant, some to the other, and you're done. And it actually doesn't affect your program at all because you were already writing an MPI program and you had already localized yourself to a quarter of the memory if you were using 4 ranks. So this maps really well to software. It's a no-brainer to use SNC4 with an MPI program, and it's just booted up that way, see if it runs a little bit faster instead of quadrant mode. I think a lot of systems will be booted in quadrant mode all the time. I know that Cray, at their place, they boot some of the nodes in some modes, some in others, and just run applications based on that. I don't know all the different solutions people may have. but that we're learning with applications what runs faster where. But this is a reconfigurability of the system to either boot it up to be as if it's one big NUMA zone, 2 NUMA zones, or 4. That's ultimately what cluster modes allow. And if you're running it as one NUMA zone, the access time to all of memory is the same, but it's slightly higher than if you're running it as 4 NUMA zones, in which case you get slightly better performance in your own quadrant and slightly worse performance if you access memory outside. Really important to know on Knight's Landing, memory is always completely coherent across the entire device. That is never broken in any of these modes. The only issue is whether we optimize for accessing memory in our own quadrant or in the 2 modes in the hemisphere, but optimizing in your own quadrant, or if we optimize the performance across the whole chip. Again, it's a boot time option because these are the decisions that usually would be made by architects when we design the chip and hard-coded, but we, in Knight's Landing, made it flexible. So cache, I think cache modes are interesting for applications, the cache versus using it as memory for MCDRAM. I think some programmers will try using it, managing the memory themselves, and that has implications for the application. Cluster modes, I don't think, are very much of an application issue. I think if you are using MPI, dividing up into ranks, you probably should try SNC2 or 4 mode and see if you get a performance boost out of running the machine that way, but I don't think you'll change your application for cluster modes. I think this will be a case of booting the machine in a mode that matches your application rather than changing your application for the machine. Now, one other thing that's, you know, these, I mentioned before that the tile are a distinct unit you can see on here, and the tile have 2 cores on them. One of the interesting questions is how many tile are there? Intel has said that Intel will sell Xeon Phis or Knight's Landings with up to 72 cores. That would suggest using 36 tile. But if you actually take a look at the photo that Intel released, there are 38 tile. And you might say, what's up? Well, if you went and looked at a memory chip and looked at how many lines of data are in a memory chip, you would always find that there are extra lines. And the reason is, when you get a circuit this large and complex, there needs to be some redundancy in order to up yield that you can turn some things off if they turn out to not have been manufactured correctly. Call it a defect, but a defect takes many different forms. It can be a malformed transistor. It can also just be slow transistors, but something that doesn't run to spec. So Intel's announced, I think they have development machines with 64 cores, and they have other machines with 68. You know, with the original Xeon Phi, there were 57 core, 60, 61, and 62 core versions. This one will be no different. There will be some 72 core versions as well. But I know that there's already 64. In the book, we use 64 and 68 core devices. Here's where hemispheres are interesting. 68 is not divisible by 4. So the problem is, or not divisible by, let's get this right. So if I try to divide 68 by 4, see, you'll find out my math is really slow. We get 34 when we divide by 2, and then we get 17 when we divide by 4. The problem is 17 doesn't fit on a set of tile. Maybe I should have said it doesn't divide by 8, but the problem is you can't take, if you do 68 cores, that means if you try to divide into quadrants, you're going to end up with 9 tile, 9 tile, 8 tile, and 8 tile. So 18, 18, 16, and 16 cores. You can't do 17, 17, 17, 17. So you're going to see some machines designed with 68 core devices, and using the quadrant or SNC4 modes may not make as much sense because you'll have unbalanced the number of cores in your quadrants. So I think you'll see people on those machines use hemispheres, which is dividing by 2, so that they could do 34 core and 34 core in the halves. Because you have to, when you divide the chip up in quadrants or hemispheres, you're actually dividing up tile, not cores. And the tile have to be in one quadrant or in the other. And so that's why you'll see people use the hemisphere or SNC2 modes on devices where the number of cores, if you divide it by 4, would be odd, because an odd number would indicate that you can't map that onto a set of tile. Anyways, on this design, Intel is able to ship devices with a certain number of active cores. A defect in the L2 or the VPUs or the CPUs would shut a tile down, but the tile, or actually not the L2s, but the tag directories, the L2 gets shut down. The tag directories and the caching agent and the routing has to work on all the tile. Again, just thinking as an engineer, how would you design this? You can't have a tile go completely dead. So you can have defects in some areas, but the routing has to work through a tile, and the caching agents and so forth are designed to all be working. But that greatly reduces it greatly reduces the number of transistors to have to work in a tile if you're turning that tile off. Anyways, this is a very common design thing. I bring it up because everybody faces this. GPUs have rows and things they can turn off and on. Memory devices do. Multi-core chips do as well. One of the important things in the design is when you turn off a tile, you also turn off its power consumption, because it's not very good if you leave it on. It keeps consuming power